Have you ever watched a basketball soar through the air, a graceful arc against the backdrop of the court? These everyday phenomena hint at a fundamental concept in physics: projectile motion. Understanding its principles unlocks a deeper appreciation for the world around us. Think back to that basketball soaring toward the hoop. Its motion isn't random, it's governed by predictable laws. This is the allure of understanding projectile motion. Our journey begins centuries ago with Galileo Galilei. He challenged Aristotle's belief that objects fall at speeds proportional to their weight. Galileo unveiled that horizontal and vertical motions are independent. Dropping a cannonball and firing another horizontally both hit the ground simultaneously. This insight revolutionized our understanding of motion. A football pass follows a curved path, showing independent motions at play. Now, let's delve into the heart of projectile motion. Any object launched into the air, whether it's a baseball, a rocket, or even a simple pebble, becomes a projectile. Its motion is governed by a fascinating interplay between its initial velocity, the angle of projection, and the ever-present force of gravity. Imagine throwing a ball at your friend. The initial velocity, the speed and direction at which you release the ball, plays a crucial role in determining the projectile's path. A faster throw results in a longer trajectory, while the angle at which you throw dictates the height and distance the ball will travel. Think of a firefighter aiming a hose at a blazing building. The angle at which the water stream is directed significantly impacts its effectiveness. A steeper angle might reach higher floors but cover less horizontal distance. Conversely, a shallower angle maximizes horizontal reach but might not reach the upper levels. While the initial velocity sets the projectile in motion, it's the relentless force of gravity that shapes its elegant arc. Gravity constantly pulls the projectile downwards, influencing its vertical motion and ultimately bringing it back to the ground. Imagine a basketball player taking a free throw. As the ball leaves his fingertips, it travels upwards, seemingly defying gravity for a brief moment. However, gravity's influence is ever present, gradually slowing the ball's ascent until it momentarily stops at its peak height. From this peak, gravity takes over, pulling the ball downwards, causing it to accelerate until it reaches the ground. This constant tug-of-war between the projectile's initial upward motion and gravity's downward pull creates the characteristic parabolic trajectory we observe. Think of a water fountain gracefully arching its watery display. The water droplets, initially propelled upwards, follow a graceful curve as gravity pulls them back down, creating a mesmerizing spectacle of motion and form. Pause 3s. Now that we've explored the physical aspects of projectile motion, it's time to delve into the mathematics that govern these fascinating trajectories. Understanding the equations and formulas behind projectile motion not only demystifies the phenomenon, but also empowers us to predict and analyze it with precision. Let's start with the formula for the maximum height. H, a projectile can reach. This can be expressed as h equals v02 assigned to fifth 2g. Here, v0 is the initial velocity, phi is the launch angle, and g is the acceleration due to gravity. This formula illustrates how the initial vertical component of the velocity and the gravitational pull determine the peak of the projectile's arc. Next, let's look at the range r of the projectile, which is the horizontal distance it covers. The range can be calculated using r equals v02 santin utipo bumam kirkin kinsintotin g. This equation shows that both the initial velocity and the launch angle play crucial roles in determining how far the projectile will travel. Now, let's consider the total time, t, the projectile spends in the air. This can be derived from the vertical motion equations and is given by t equals kamon idi asin 2 synth plus g. This formula highlights the influence of the initial vertical velocity and gravity on the duration of the projectile's flight. To better understand these formulas, let's visualize them with some illustrations. Imagine a cannonball being fired at different angles and velocities. As we adjust these parameters, the peak height, range, and flight time of the cannonball change accordingly, following the precise predictions made by these equations. By breaking down these formulas and their derivations, we gain deeper insights into the intricate dance between velocity, angle, and gravity. This mathematical framework not only enhances our appreciation of projectile motion, but also equips us with the tools to analyze and predict it accurately. Pause 3s. With a firm grasp of the mathematics behind projectile motion, we are now ready to further dissect the trajectory and uncover the secrets of range in the next chapter. To truly understand projectile motion, we need to dissect its trajectory, the path it traces through the air. This path, as you might have guessed, is not a straight line, but a graceful curve known as a parabola. Imagine drawing a line connecting all the points the projectile occupies during its flight. This line, my friends, is the trajectory, a visual representation of the projectile's journey from launch to landing. The parabolic shape arises from the interplay between the constant horizontal velocity and the changing vertical velocity due to gravity. Think of a golfer teeing off on a vast fairway. The golf ball, struck with precision, soars through the air, its trajectory a gentle parabola against the backdrop of the sky. This curved path is a testament to the independent horizontal and vertical motions working in perfect harmony. Now, let's talk about range, a crucial concept in projectile motion. Range refers to the horizontal distance a projectile travels before returning to its initial launch height. Understanding range is crucial in various fields, from sports to warfare, where maximizing or predicting distance is paramount. Imagine a javelin thrower at the Olympics, their eyes on the prize as they launch their javelin with impressive force. The javelin, a projectile in its own right, sails through the air, its range determined by a delicate balance of factors. The initial velocity, the angle of projection, and even air resistance all play a role in determining how far the javelin will travel. A higher initial velocity and a launch angle closer to 45 degrees generally result in a greater range, assuming ideal conditions. Think of artillery units during historical battles, carefully calculating the angle and power needed to launch cannonballs at enemy lines. Their understanding of projectile motion, particularly the concept of range, played a pivotal role in determining the outcome of battles and the course of history. One of the most remarkable aspects of projectile motion is our ability to predict it with astonishing accuracy. Armed with the laws of physics and a few key parameters, we can chart the course of a projectile, foretelling its every move before it even happens. Let's delve into the derivation of the trajectory equation. The path of a projectile is a parabola, described by the equation y(x) tan theta, frac gx2 2v02 g squares 2 e theta. Starting with the horizontal and vertical components of motion, we use xv0 plus cos plus theta t and yxv0 e p sine plus theta t, frac /1 2 gtl2. By eliminating the time variable, te, we derive the trajectory equation, which allows us to predict the projectile's path. Using this equation, we can determine key parameters like the maximum height, h equals frac v0 u2 sin l2 is theta 2g, and the range, r is above frac v0 2 plus sin 2 plus theta g. By plugging in the initial velocity, launch angle, and other relevant factors, we can calculate with precision the projectile's position, velocity, and acceleration at any given moment in time. Think of astronomers tracking the movements of celestial bodies, their telescopes peering into the vast expanse of space. By applying the principles of projectile motion on a cosmic scale, they can predict the trajectories of comets, asteroids, and even entire galaxies, unraveling the secrets of the universe one equation at a time. The applications of projectile motion extend far beyond the confines of textbooks and classrooms. Its principles are woven into the fabric of our world, influencing everything from the way we play sports to how we explore the cosmos. Imagine a baseball game in full swing, the crack of the bat echoing through the stadium as a batter sends a high fly ball soaring towards the outfield. The outfielder, intuitively understanding projectile motion, tracks the ball's parabolic arc, positioning himself perfectly to make the catch. From the precision of archery to the calculated arc of a basketball free throw, projectile motion is an integral part of countless sports, adding an element of physics to the thrill of competition. But the applications of projectile motion extend far beyond the realm of sports. Military strategists rely on its principles to develop accurate artillery systems, while engineers utilize it in designing everything from bridges to airplanes. And of course, space exploration, the ultimate frontier, hinges on our mastery of projectile motion. As we delve deeper into the intricacies of the universe, our understanding of projectile motion serves as an indispensable stepping stone. The concepts we've explored here form the foundation for more advanced topics in physics, mechanics, and beyond. Imagine a student captivated by the elegance of projectile motion, eager to unravel the complexities of the universe. Their journey into the world of physics, fueled by a solid understanding of motion, opens doors to exploring concepts like work, energy, and momentum. The principles of projectile motion, particularly the independence of horizontal and vertical motion and the influence of gravity, provide a framework for comprehending more complex phenomena, such as orbital mechanics and the behavior of objects in non-uniform gravitational fields. Think of physicists studying the motion of subatomic particles, their research pushing the boundaries of our understanding of the universe. Even at these incredibly small scales, the fundamental principles of projectile motion, albeit with modifications to account for quantum effects, still hold sway. As we conclude our exploration of projectile motion, take a moment to appreciate the beauty and elegance of this fundamental concept. From the graceful arc of a basketball to the awe-inspiring trajectory of a rocket launching into space, projectile motion surrounds us, shaping our world in countless ways. Understanding projectile motion isn't just about memorizing equations or solving textbook problems. It's about developing a deeper appreciation for the intricate dance of objects in motion. It's about recognizing the influence of physics in our everyday lives and marveling at the predictability and elegance of the universe we inhabit. So the next time you witness a projectile in flight, whether it's a bird soaring through the air or a child tossing a ball, take a moment to appreciate the unseen forces at play. Remember the principles we've explored, the interplay of velocity, gravity, and trajectory, and let your curiosity soar as you continue to explore the wonders of the physical world. Our journey into the realm of physics has just begun, and the possibilities for discovery are limitless.